Think of the scariest thing in the universe. A place where gravity is so terrifyingly strong that not even light, the fastest thing in existence, can escape. A monster that swallows stars whole and erases everything it touches. We've all been told the exact same rule about black holes. Nothing ever gets out. It's cosmic rule number 1. Once you cross that border, the event horizon, you're gone forever. End of story. Except, what if that rule is completely wrong? What if black holes aren't permanent monsters at all? What if they are slowly leaking, losing weight, and shrinking until they vanish into a blinding explosion? In 1974, a physicist in a wheelchair named Stephen Hawking dropped a theoretical bomb on the scientific community. He proved that black holes don't just eat, they glow, they bleed heat, and eventually they die. Welcome to Horizon's Edge. Today, we're unpacking one of the most mind-bending secrets of quantum physics, Hawking radiation. And I promise you, by the end of this video, you will never look at a black hole the same way again. To understand how a black hole can leak, we first have to fix a giant misconception about empty space. If you take a box, pull out all the air, block all light, and drop the temperature to absolute zero, what's left inside? Nothing, right? Total vacuum. Well, quantum mechanics says, nope. Vacuum is never empty. If you could zoom in with an impossible ultra microscope down to the subatomic scale, space is actually boiling like a hyperactive foam. Millions of tiny particle pairs are constantly popping into existence out of pure energy, holding hands for a tiny fraction of a trillionth of a second, slapping into each other and vanishing back into nothingness. We call these virtual particles. One has positive energy, one has negative energy. They borrow energy from the universe, exist for an instant, annihilate each other, and pay the debt back. Net energy change? Zero. Nature keeps the accounting books perfectly balanced. This happens right now in the room you're sitting in. It happens inside your body. It happens everywhere in space. Now, what happens when this quantum chaotic foam takes place right on the edge of a black hole? That's where things get wild. Imagine two twin runners holding hands, standing right on the edge of a steep cliff. Suddenly, a giant gust of wind pulls one twin over the edge into the abyss, while the other twin gets blown back onto solid ground. Because they were separated, they can never meet to annihilate each other. This is exactly what happens at the event horizon, the point of no return. A pair of virtual particles pops into existence right on the razor-thin boundary of the black hole. Before they can recombine and disappear, gravity tears them apart. One particle falls down into the black hole, but the other particle escapes into deep space. Now wait, you might say, okay, cool, the black hole swallowed a particle, so shouldn't it get bigger and heavier? Here is Stephen Hawking's genius breakthrough. For the escaping particle to become real, permanent energy out in space, the particle that fell in must carry negative mass energy. When the negative energy particle gets swallowed, it actually subtracts weight from the black hole. To an observer sitting far away with a telescope, it looks like the black hole just emitted a warm, glowing particle out of nowhere. But in reality, the black hole just got tricked into paying the energy bill. It traded a piece of its own mass to launch that particle into space. So, black holes are on a mandatory weight loss diet. Every second of every day, they radiate away their mass bit by bit. This escaping energy is what we call Hawking radiation. But here comes the weirdest, counterintuitive twist in all of physics. Normal things cool down as they lose energy, right? A hot cup of coffee gets colder. A fire burning out gets dimmer. Black holes do the exact opposite. The smaller a black hole gets, the hotter and faster it radiates. A supermassive black hole at the center of a galaxy is super cold, colder than empty space itself. So it evaporates at a painfully slow crawl. It would take more than 1,067 years to evaporate. That's a 1 followed by 67 zeros, longer than the current age of the universe. But as the black hole loses mass, its gravitational grip near the horizon gets tighter, its temperature skyrockets, and the evaporation rate goes crazy. In its final seconds, a tiny dying black hole will release as much energy as millions of hydrogen bombs exploding at once. It vanishes in a flash of pure gamma-ray light. Now, why did Hawking radiation make physicists sweat and argue for 40 years? Because of a massive clash between general relativity and quantum mechanics known as the black hole information paradox. In quantum physics, there is a fundamental rule. Information can never be destroyed. If you burn an encyclopedia, theoretically, if you collected every atom of smoke, ash, and heat photon, you could rebuild the text. The history of those atoms is preserved. But if you throw an encyclopedia into a black hole, and the black hole completely evaporates into featureless Hawking radiation, where did all that information go? Was it permanently erased from reality? If information can be destroyed, quantum physics breaks down. If information cannot be destroyed, Hawking's math has a hole. This conflict started a 40-year cosmic war between theoretical physicists that led to groundbreaking theories like holograms and quantum entanglement. Isn't it incredible? The most terrifying objects in our universe aren't immortal black vaults. They are dynamic, breathing quantum engines that glow in the dark, age over trillions of years, and eventually return their energy back to the cosmos. Stephen Hawking showed us that even where light itself is trapped, there is still a way out. Here on Horizon's Edge, we believe one simple truth. Science isn't complicated. Most of the time, it's just poorly explained. If you enjoyed this journey to the edge of space and time, hit that like button. Drop a comment with the next cosmic mystery you want us to unravel, and don't forget to subscribe. Keep asking questions, keep looking up, and I'll see you at the next horizon.